All right, our first speaker of the day is Alex Cole, who will be telling us about a new spin on the weak gravity conjecture. Take it away, Alex.
Great, thanks, Cody, and thanks, Cody and John in general for organizing this series and giving me this opportunity to talk. So in this talk, we're going to try to understand the weak gravity conjecture. And this is based on some work that the latest paper came out in November with Lars Aalsma, Greg Logis, and Gary Shiu. So here's an outline for this talk. We'll start by reminding everyone of the swampland idea, and in particular, the weak gravity conjecture and its mild form, which concerns black holes and their horizons and corrections to black hole horizons, to try to kind of, from the perspective of trying to understand the weak gravity conjecture, I'm going to kind of describe what is happening to the horizon in the mild weak gravity conjecture. Then we're going to move kind of beyond the horizon as we try to understand why horizons are corrected in the particular weak gravity way we want, which will lead us to a covariant condition for the mild weak gravity conjecture. We'll apply this to some interesting examples, including the BTZ geometry, which is in part interesting because ideas of entropy and monotonicity appear. And so we'll be able to make contact with weak gravity-like behavior and a holographic c-theorem in this case. So moving on, finally, we'll try to see whether this can illuminate at all the charged black hole weak gravity conjecture. So BTZ is in part interesting because it can arise via certain limits, the near horizon limit of a 5-dimensional black string. And so we'll see how the weak gravity conjecture for the BTZ relates to a charged black hole that is in the dimensional reduction of this black string, which will lead us to formulate this total landscaping principle, sort of saying that we want to apply consistency conditions to every dimensional reduction and compactification of our system. And then we'll wrap up. So it's well known to this audience that consistent ultraviolet physics constrains infrared EFTs. And in particular, when the UV is quantum gravity, this is the swampland program. What we're interested in doing as string phenomenologists is separating the landscape from the swampland. And to do this, we want to use precision tools where we have lots of control, like supersymmetry and extremal black holes. Okay, so here is the cartoon picture that we're very familiar with. We have quantum gravity at high energy scales, and at low energies, we just see effective field theories, and we want to find the boundaries between the landscape and the swampland here. So as I mentioned, we're most interested in this talk in the weak gravity conjecture, which is one of the most famous swampland conjectures. And the weak gravity conjecture quantifies quantum gravity's objection to trying to take the global symmetry limit of a gauge symmetry. Our practical definition of the weak gravity conjecture for this talk is we're going to say that we want to allow the kinematic possibility of extremal black hole decay. Okay, so black holes, if you want to give them some charge, there is an upper bound on this charge at fixed mass. We call this an extremal black hole. If you try to add more charge, then you will create a naked singularity, which we don't like. So to allow this extremal black hole with Z equals 1, charge to mass ratio equals 1, what we need are Z greater than 1 states in the theory. So here's the cartoon of some black hole decay. So perhaps we end up with a sub-extremal black hole and what we might call a weak gravity relevant state. And in this picture, we can kind of be agnostic about whether this state with Z greater than 1 is a particle or a black hole. So in fact, the latter case is relevant in string theoretic examples. So what we can do is actually have the super extremal state be a black hole. And this is allowed if we modify the extremality bound of the theory, which is something that happens generically. We say that we need to compute corrections to the extremality bound, and these corrections allow for black hole decay. So this is called sometimes the mild form of the weak gravity conjecture, because the weak gravity relevant states are very heavy. But in certain circumstances, you can try to strengthen it by using symmetries of partition functions and whatnot. So focusing on this mild form of the weak gravity conjecture, we naturally draw some relations with the positivity literature. So let's look at an example where we have Einstein-Maxwell theory at the two derivative level, and we expand to leading order in higher derivatives. So we have these four derivative terms in a particular basis. We have an f to the fourth term and ff term, and the Wilson coefficients a1 and a2. So you can compute that the shift in charge to mass ratio of the temperature equals 0 state in this theory depends on a particular combination of these Wilson coefficients, namely 2a1 minus a2 over this normalization factor. And for weak gravity compatible behavior, we want this, this to be positive. So this will allow extremal black holes to decay into smaller extremal black holes. So these Wilson coefficients are interesting to people outside the swampland as well. They're interesting from the perspective of unitarity and causality, consistency conditions of our theories. And unitarity and causality can constrain Wilson coefficients. But what has become clear in recent years is that more ultraviolet information is needed to prove the weak gravity conjecture. So unitarity and causality alone are not sufficient. We need to understand something about the ultraviolet in cases that we've seen. So from this kind of line of work, we're led to ask the question, what is the minimal set of assumptions we need to make to prove the mild weak gravity conjecture? And what are the deep reasons that it should be true? To try to illuminate this, we can ask for kind of a physical picture of what's happening in the mild weak gravity conjecture. So let's look at a typical black hole in Schwarzschild gauge. So this is the gauge that is most familiar for a black hole metric. So we have this function f of r. And f of r tells us about the horizons of the black hole. For a subextremal black hole, f of r hits 0 twice. It goes down and comes back up. For an extremal black hole, f of r just kisses 0, the 0 line. So in terms of this picture, we can talk about the horizon of a black hole and sort of formulate it visually. What we want is that the state that is extremal in the two derivative theory, so m equals q, and therefore temperature equals 0, f of r takes this form. We want this state with the same charges, m and q, to now have positive temperature once we take into account higher derivative terms. And so this means that this blue curve shifts down to this orange curve. So in other words, if we fix the charges of the states that we're considering, the statement of the weak gravity conjecture is that the entropy shifts positively. Now, there's a nice argument that was, as far as I know, first written down by Yuta, Toshifumi, and Gary, that the change in the entropy in this case scales as the shift in the area of the black hole, which in this particular case goes as the square root of the Wilson coefficient. So this dominates over what you might call like walled corrections or explicit corrections. So this is the statement of what's happening to the black hole horizon in a weak gravity satisfying theory, high derivative corrections. Alternatively, so this is equivalent to the statement that the shift in extremality at fixed temperature is greater than or equal to 0. So it's important when talking about these black holes and their corrections to be explicit about what is being held fixed. And we're going to talk about things in terms of both of these quantities, shifts in entropy and at fixed charge, and shifts in extremality at fixed temperature. Okay, so this is weak gravity satisfying behavior. We might ask, what are the physical reasons that corrections might give you this behavior? So this leads us to a covariant condition for the mild weak gravity conjecture. The correct way to talk about charges in a generally covariant theory is the Ayer-Wald formalism, which describes off-shell variations of Hamiltonians associated with surface charges. I'm not going to show the derivation to you, but you can read our paper. that there is the following formula where you look at variations of some solution. So on the left-hand side, we have these two integrals of a particular variation of a Hamiltonian. This Hamiltonian is associated with a killing vector in the theory. The first integral is an integral over infinity. And what we get from this integral is the variation of some asymptotic charge. The second integral is over the black hole horizon. And so what this contributes to the formula is some correction to the behavior at the horizon of the solution, or the entropy. And the right-hand side is about the corrections that we're adding. So what we have is you can take the higher derivative terms and write them as an effective stress tensor, an effective shift in the stress tensor of your solution. And we take the inner product with the killing vector and also another vector that is normal to a particular slice. So we slice and go from the horizon to infinity. This is essentially, you use Stokes' theorem to derive this. And so we evaluate this formula on an extremal black hole background with a judicious choice of the killing vector. And generally, we're going to hold the charges fixed. I'll show you an example on the next slide to make this a little more explicit. I just want to point out that in practice, this is a computationally convenient condition for evaluating the mild weak gravity conjecture. In particular, you don't need the explicit form of the corrected solution. So that's quite nice. I also want to point out that in terms of corrections to black hole horizons, a non-covariant version of this argument, essentially this argument just in Schwarzschild gauge, appeared in this early work from 2006, I believe. So let's look at what's actually that example in this case. So an electrically charged black hole in 4 dimensions. So we start with our uncorrected solution, and I'll write it in Schwarzschild gauge in this case. So we have the metric as well as a gauge field. I've pasted the forms of 2 Hamiltonians here, although they're not particularly illuminating. This is just to show that you derive these expressions and then throw them into these integrals. So we take these Hamiltonians. One of them is associated with the time-like killing vector of the geometry, and therefore it gives us, when we evaluate over infinity, a variation in the mass of the state. The other one, and I've kind of swept this under the rug just for sake of time, is associated with gauge transformations. And this, when we integrate over infinity, tells us about a variation of the electric charge. So if we take the formula on the previous page and evaluate at fixed charge, so with delta M and delta Q equal to 0, the remaining term is just from this correction to the horizon. And so we find this thing, delta F at the horizon, and F is our kind of very special function in Schwarzschild gauge, which is then equal to this integral of some effective stress tensor. And for the weak gravity conjecture in its mild form to be satisfied, we need this to be positive. So in other words, the solution at M equals Q becomes positive temperature, which is the same as saying the shift in the horizon at Z equals 1 fixed is greater than 0. So in particular, we look at this theory, which I showed earlier, in fact. And so what we compute is that delta F plus these delta M and delta Q, which if we fix the charges of our scenario are 0, scales as essentially just computing the stress tensor of these terms, which gives us the same bound that I mentioned earlier. So we have this sense in which entropy corrections must take a particular sign. And so this leads us to want to talk about things like monotonicity and so on. And so we're going to move to now 3-dimensional gravity. So we consider the three-dimensional Lagrangian for ADS3 gravity. So here's our cosmological constant, R, and then we have two higher derivative terms in this case. So three-dimensional ADS gravity admits black hole solutions. These are the BTZ black holes. And rather than being electrically charged, these black holes have angular momentum. So they have some J. And this leads to, again, some possibility of giving them too much charge, too much angular momentum. So there's an extremality bound, J over M. And if you compute this extremality bound in the presence of higher derivative terms, you find that the correction goes in this way. So one of the nice things about ADS3 gravity is that because of holography, we have this two-dimensional CFT to look at, and we can compute corrections to the CFT's central charge. And what we find is the same combination of Wilson coefficients in this case, but in terms of signs, this is a minus sign. So in other words, a positive extremality correction, delta Z greater than 0 at fixed temperature equals 0, corresponds to a negative central charge correction. So delta C decreasing, delta C is negative. So this is in part interesting because we have some theorems about central charges in two-dimensional quantum field theories. In particular, if you start at a CFT and apply a relevant deformation, and then this triggers an RG flow, if you end at a CFT in the infrared with some other central charge, C prime, then the c-theorem tells you that the central charge of the infrared theory is smaller than the central charge of the ultraviolet theory. So this, if you remember the previous slide, is what we might call weak gravity-like behavior. So in particular, if we consider the following setup, we take ADS3 gravity and we couple to some light matter. This will take the configuration that is an extremal black hole off shell. So what you do then is radially you solve the equations of motion, which is holographically dual to this RG flow in the boundary theory. What you find is in the infrared, you have a corrected extremality bound, where now we just have this number and C minus C prime. And so the interesting thing perhaps to note is that in this case, the null energy condition along the RG flow in the bulk, I should say, implies weak gravity-like behavior. So, this is like the weak gravity conjecture, but for black holes with angular momentum. So you might ask, do we need such a conjecture? And we can speculate on this slide. So there have been arguments related to black hole thermodynamics about the weak gravity conjecture. These are, of course, insensitive to the nature of the charge that we're giving. However, in the case of spinning black holes, we know that there is the Penrose process, so extremal black holes are not really so terrible in terms of giving you problems with remnants. You might imagine that for spinning black holes, this is a generalization of some kind of repulsive force conjecture that has been put forward. If you think about spin and co-moving probe particles as experiencing, because of the centrifugal force in the co-moving frame, that if J increases for an extremal black hole, then there's somehow some enhanced repulsion. It would be kind of interesting to associate this macroscopic spinning weak gravity conjecture to constraints from the microscopic side on higher spin particles. This is more of a question mark than a bullet point. And finally, we know that for these BTZ geometries in particular, the angular momentum, so J is related to the electric charge of dimensional reductions of these higher dimensional geometries. And so we can turn and ask, how does this kind of spinning weak gravity conjecture relate to a charged weak gravity conjecture. So now let's look at 5-dimensional black strings. One nice thing, so if we look at a boosted and charged black string in 5 dimensions, there are a few interesting things you can do. One of them is to take the near horizon limit, in which case your geometry is this BTZ cross S2. Another operation you can perform is a reduction, dimensional reduction on the direction of the string. And in this case, what you end up with is a 4-dimensional charged black hole. And you can perform the entropy computations on both sides. So you can compute the entropy of the BTZ black hole, which is enabled in part by the Carty formula, or the Carty formula helps you here. You can also compute the entropy for the 4-dimensional charged black hole. So in this case, the entropies match. So you want to think of these as perhaps describing the same object. And so we can ask how the spinning weak gravity conjecture for BTZ relates to the charged weak gravity conjecture for the 4-dimensional charged black hole. So it turns out that the weak gravity conjectures for these two systems are in fact inequivalent, despite the fact that there is agreement between the entropies. So you can compute the entropy. I should say first that we are looking at this 5-dimensional Lagrangian. So we have 3 different Wilson coefficients to look at. We have an f to the 4th term, an FF term, and a Gauss-Bonnet term in 5 dimensions. So we performed these computations, and for the temperature equals 0 BTZ geometry, you can compute the corrected entropy, and this turns out to agree with the 4-dimensional temperature equals 0 entropy. However, as I mentioned previously, the temperature equals 0 entropy is not the interesting quantity for the weak gravity conjecture. So this is not going to necessarily guarantee weak gravity-like behavior. In one case, perhaps the BTZ case implies it for the other. So we compute the shift in the extremality bound for temperature equals 0 here. And in fact, for BTZ and the 4-dimensional geometry, they disagree. And so what we take this to mean, if you believe in a spinning weak gravity conjecture, is that you should combine the bounds that you get. So you can then generate this kind of plot with allowed and excluded regions. So in this case, what we are imposing are the spinning weak gravity conjecture from this BTZ geometry, as well as the 4D, the weak gravity conjecture for the electrically charged black holes in 4D, and also for 5-dimensional black holes, just for good measure. And we end up with stronger bounds. And so we ended up deciding to call this the total landscaping principle, the idea that you should enforce consistency of every compactification or near horizon limit. This is not exactly a new idea. In particular, consistency under dimensional reduction has appeared in a variety of forms in the swampland literature. But we think this is a nice name to call it. Okay, so let's wrap up. What did we do in the last 24 minutes? We reformulated the mild weak gravity conjecture as a covariant condition on the effective stress tensor of corrections, which is kind of nice, and it takes this form if you choose the right killing vector. And this is kind of interesting because you can sort of say, well, what does the stress tensor of my corrections look like? And people talk about stress tensors and their the consistencies of various theories. There are conditions on stress tensors. And we checked a few examples. For BTZ black holes, there seemed to be a spinning version of the weak gravity conjecture that follows from a holographic c-theorem in the boundary. We also looked at how BTZ geometries show up in the context of a boosted black string, which led us to this total landscaping principle that you should apply conjectures to every compactification and near horizon limit, and that for the weak gravity conjecture, this is a useful thing to do. It strengthens your constraints. There's future work. Just a few things to do are make this more rigorous about the holographic RG identification for higher dimensional black holes, and perhaps phrasing this in terms of the Hamilton-Jacobi description of holographic RG. and also to look at quantum corrections of this scenario. Thanks.
All right, thank you very much, Alex, for the very nice talk. Let's all thank Alex with our clap emojis. Are there any questions? We have one question from John.
Yeah, I just wanted to make sure I understood so it seemed like what you were saying is that you can consider these black holes or these theories in different ensembles. The t=0 ensemble and the z=1 ensemble. And regardless of which ensemble I should consider it in, I should have these weak gravity satisfying conditions. Is that right? Or
yeah, so yeah, the ensemble thing is kind of important and tricky. So I think the thing to say is that the correct statement of the weak gravity conjecture is really about extremal black holes. And so if you it's important to hold the correct things fixed when trying to phrase what you're, I don't know, proving or checking. So in fact, the weak gravity conjecture for black holes in kind of the original formulation, if you want to say like extremal black holes, we want to hold the temperature fixed at 0 and find that the charge to mass ratio increases of this state.
Under some sort of like adiabatic process, or
the tricky thing is you're kind of comparing two theories. So it's tempting from the perspective of like second law of thermodynamics to say, oh, entropy should increase. But you're comparing to, I think there's no real dynamical way to like turn on corrections in the scenario that we're interested in. So you could try to like think of some trick, but it's not obvious what the trick would be. But yeah, so I think the important thing is that if you look at the entropy correction at temperature equals 0, this is not necessarily indicative of weak gravity like behavior. So yeah, it's a subtlety that would be easier if I guess we were all a little more explicit. We try to be really explicit in the paper. But it would be interesting, yeah, to try to, in terms of this adiabatic idea, like try to come up with some experiment. Like it's tempting to say like, okay, a black hole will become bigger or smaller under some process. So I throw something in and try to make it to move in a particular way. But I think such an argument is not obvious.
okay, I think, thanks.
Thanks.
Okay, if there are no further questions, let's thank Alex again.